Hi everyone, this is going to be a walkthrough of problem 3 on CS61B Spring 2021 exam prep worksheet number 6, which covers disjoint sets and asymptotics. Okay, so before we dive into this question, I expect you guys to be familiar with weighted quick unions from lecture. If you guys haven't seen lecture yet and you guys are trying to do this question, I definitely think it's going to be on the trickier side. I did record a video walkthrough that covered disjoint sets just for a quick review, so you guys can watch that one as well. But with that in mind, let's dive in. So for this problem, we'll be addressing the asymptotics of weighted quick unions. For all big omega and big O bounds, we want to give the tightest bound possible. Okay, so if you guys want a recap of tightest bounds, I recorded a mini lecture on asymptotics, which should be linked in the second video in this playlist. Okay, so the first question states, suppose we have a weighted quick union without path compression with n elements. What is the runtime in big omega and big O of is connected? What is the runtime in big omega and big O of connect? Okay, so this is a really good example of trying to figure out tight big omega and big O bounds. So let's try to approach it first with the big O case for is connected. Okay, but before we get there, let's recall what is connected is doing. So if we have Boolean is connected, in pseudocode, how this method looks is that we return, apologies, I forgot the parameters. This is like pseudocode-esque. So suppose that we're trying to figure out if A is connected to B, okay? What we're going to return for is connected is we're going to return whether find of A is equal to find of B, right? And immediately you guys might be asking, hey Soham, what is find? Well, the function find finds the root of a given element. Okay, so recall that in a weighted quick union, we represent each component as a tree, right? So suppose that we have the following elements in our weighted quick union, 0, 1, 2, 3, 4, 5. Okay, I realize my face is probably covering that. So say we have the elements 0, 1, 2, 3, 4, 5 in a weighted quick union. Okay, let's say that we have one group containing the elements 0, 1, 2, 3. How we could potentially have a tree that captures this group is, let's say we have the tree 0, 1, 2, 3. Okay, so looking at this group, if we ever call find on 3, this will give us 0, right? If we call find on 2, this would also give us 0, right? In other words, if we call find on any element of this tree, right, we will always get the root of the tree. That's what the find operation is doing, okay? So is connected, all it does, it calls find on A, find on B, and it checks if these are the same root, right? In other words, what we're doing in is connected is we're asking, do A and B belong to the same tree? To verify if they belong to the same tree, we just make sure that they have the same root. So with all of this in mind, to approach the runtime of is connected in the worst case, actually I take that back, to find a tight big O bound, we should try to think about what could take the most amount of time, right? To take the most amount of time, in this case, would probably be find of 3. Because in order to find the root of the 3, we would have to iterate all the way up the tree. And that is more iterations than 2 and 1 are doing, okay? So to generalize this, in any case, in order to have the most work possible, we would call find on the bottom of the tree, right? So to maximize work, we call find on A, where A is at the bottom of the tree. Okay? So if A is at the bottom of the tree, what is the maximum height this tree can possibly be? Okay, so the maximum height this tree can possibly be is going to be log n. Okay, I'll give you guys a quick intuition on why this is the case. So in order for us to ever double the height of a given tree, or I take that back. In order for us to ever increase the height of this tree by 1, what we have to do is we have to merge it with a tree of the same size, or of the same number of elements inside it, right? What I mean by that is, suppose that we have this tree, okay? If we ever call connect, where we pass in this tree, and then we pass in another tree, let's just say it has values 4, 5, 6, 7. Okay, notice that if we ever call connect on 4 and 0, what's going to happen here is that the height of the resulting tree will be 1 greater, right? And what we'll see is that in order for us to ever increase the height of a connected component, we need to connect 2 components of the same size. So what this is saying is that in order to increase the height by 1, we need to double the size of the tree. Okay? I'm going to write that down because this is why we have a log n relationship for the height. So in order to increase the height by 1, let me put this in here. In order to increase the height by 1, we need to double the number of elements in the tree. Okay, so intuitively, we can reason that if it takes doubling the number of elements in the tree to increase the height by 1, the maximum height that we could possibly have in any weighted quick union connected component tree is going to be log n, right? So what we can say is that this is log n in the worst case, right? It's not necessarily always log n, right? Because we could potentially have a tree that looks like everybody connected to the root, right? This is a totally valid tree. So in the worst case, the maximum height of a tree is going to be log n. Finally, what we can say with all of this being done is that the tightest big O bound we can give for is connected is going to be log n, because in the case that takes the most amount of time, right, what we're doing is that we call find of a where a is at the bottom of the tree, in which case the total amount of work that we're doing is the height of this tree, which we know in the worst case is log n. Okay, so the easier way of approaching, the easier part of the first part of the question is the omega bound. Okay, so I'm going to quickly get rid of some of this work just to clean things up, because it's a little scary right now. Let's get rid of there. Okay, so we're back to a reasonable state of the given board. So to find the tightest big omega bound, we should ask ourselves, what's the situation where this function executes as fast as possible? So suppose that a and b are both roots of the respective components. What I mean by that is, suppose we call is connected. Let's say this is the current state. If we have 1, 2, 0, 1, 2, 3, 4, 5, 6, and the groups are 0, 1, 2, 3 together, and then 5, and then 6, And let's just put 4 here. Okay. So what we can see is that the groups that we have are 4 and 6, 0, 1, 2, 3, and then 5 is by himself. Okay. So if we ever call is connected on 0 and 6, notice that the amount of work that find does is constant since we're already at the top of the tree. So in this case, the tightest big omega bound we can give is big omega of 1, right? Okay. So now what I'm going to do is when we're looking at connect, let's recall what connect does. Okay. So if we have connect of AB, what we do is that we find the root of the tree A belongs to, we find the root of the tree B belongs to. So let's say root A is equal to find A, root B is equal to find B. Then what we do is we decide which root is smaller. What I mean by that is which root belongs to a tree that's of a smaller size. Let's take that root and make it a child of the other one. So set smaller root as child of the other. Okay, so this is basically what connect is doing. So what we're going to notice here is that this operation runs in constant time, right? So the only amount of work that we actually do in connect comes from find A, find B, right? Which is the exact same work that we're doing in is connected, okay? So what we can say is that connect has the same big O and big omega runtime as is connected because it's essentially performing the same operations, right? And appropriately, I can give it the same bounds. Okay. So that is all for part A. I hope that was helpful. Let's move on to part B. So this part is a bit confusing, so I'll try to explain intuitively what the question is asking. But first, let's read the prompt. Suppose for the following problem, we add the method add to WQU to the WQU class. Simply put, the method takes in a list of elements and randomly connects elements together. Assume that all the elements are disconnected before the method call, and the connect method works as described in lecture. So to recap, what this method is doing intuitively is that we have a bunch of elements that belong to a weighted quick union, say 0, 1, 2, 3, 4, 5 in this example. What we're going to do is we're going to randomly connect these elements together, okay? How we're going to achieve that is we're first going to find all possible pairs of these elements, okay? So what does that mean? If we're looking at this example right here, if we call pairs with 1, 2, 3, supposing that elements is 1, 2, 3, the total amount of pairs are going to be 1, 2, 1, 3, and 2, 3, okay? So all that pairs is doing is it's outputting the total number of unique pairs involving the elements in elements, okay? We'll come back to the pairs method in a few seconds. But first, once we have all of these pairs, right? In this example, it's 1, 2, 1, 3, 2, 3. What we're going to do is we're going to call shuffle, which reorders randomly these pairs. In this case, a potential reordering is as follows, okay? So the last thing that we're going to be doing is we're going to iterate through all of these pairs. We're going to call connect of the first element of the pair, and we're connecting it to the second element of the pair, okay? So in essence, just to recap, what this function is doing is it takes in a bunch of elements. It's going to call at some point connect on every pair of elements. The order in which it calls connect is random, and that randomness comes from shuffle. Okay, with all of this in mind, let's try to figure out some way of approaching the runtime of add to weighted quick union in big O. Okay, I think this problem is really good because it kind of combines the asymptotics we were talking about earlier with weighted quick unions. So how do we want to approach this is that we want to decompose the following function into specific parts and figure out how much time each part takes, okay? So we know that both of these parts take constant time, and that's because we assume so in the problem statement, okay? So the only work that this function is actually doing really comes from this for loop, okay? So the next question I have for all of you is how many times does this for loop execute, okay? So if you guys are watching, stop the video, think about it, and I'll be going over the answer right now. So the number of times this for loop executes is equal to the number of pairs, right? So what is the total number of pairs we can have in an array elements of length n, okay? So suppose that we have such an array. I'm going to generalize this to an example where the elements array is of length n. Okay, so say that we have the following array. The total number of pairs we can have, let's assume that every time we make a pair, the number on the left is less than the number on the right, okay, as shown with these examples. So what I mean by that is that in all the pairs, if we ever have a pair x, y, x is always less than y. Okay, and the reason we can make such a claim is that it states the pairs method returns an ordered array of all unique pairs, which is telling us that the pair 3, 2 will never exist if 2, 3 is already there because we have unique pairs. Okay, let's jump back to the question we were trying to answer, which is how many pairs are in this array, right? What is its length? So what I'm going to say now is that let's consider all of the pairs where 0 is the first element, okay? 0 is going to be the first element with 1. It'll be the first element with 2, and it'll be the first element with everybody until the end, okay? Now let's look at all of the pairs where 1 is the first element, right? I'm going to make this a little more pictorially correct. Okay, so what we're going to notice here is that 1 is the first element in pairs with elements that are farther than it in this array, right? So what we can say is that 1 is going to be the first element. In this example, we have, let's just make this n minus 1. So there's n elements in this array. I just want to make the numbers a little more accurate. There's n elements in this array, and the last element is n minus 1. So what we can say is that 1 will be the first element in a pair with n minus 2 other people. Okay? We could think about 0 will be the first element in a pair with n minus 1 other people. Okay? Do you guys see that? The reason is because 0 is going to be the first element in a pair with everybody that's later than it in the list, okay? So the total amount of pairs that we will have is going to be the sum of n minus 1 plus n minus 2. These are all of the pairs that 0 is the first element. These are all the pairs where 1 is the first element. Plus, we can kind of extrapolate this logic to see that it's going to be the following sum, right? And what we're going to notice now is that this sum is the equivalent of the sum we saw earlier, right? It's the same sum. All I did here is I just added an n at the end, which doesn't really change anything asymptotically. So what we know is that this sum is equal to n squared asymptotically, okay? Finally, what we know is that the number of times this for loop executes is equal to the number of pairs, which is on the order of n squared, okay? That was a really long explanation, but I think it's really helpful to prove all of these things to yourself. So if this for loop is getting executed n squared times, how much work will each connect call take? Okay, so what I'm going to show now is that from the previous example, we know that connect in the tightest big O bound is big O of log n, right? So what we can say now is that if we have n squared times this for loop is executed, and each time we call connect, it can take at most log n time, what we can say a valid big O bound is going to be n squared log n, okay? So this is a valid big O bound. Now I'm going to show that it's the tight big O bound, okay? Just to recap, this is a valid big O bound because this for loop gets executed n squared times. Each time in the for loop, we can execute at most log n work, right? So what we can say here is that a valid big O bound is n squared log n. So let's now show that this is as tight a big O bound we can possibly get, okay? So let's construct such an example where we have a total of n squared times connect is called. Okay, let's say that the first n times are meant to construct a tree of height log n. Okay, so this is possible. So the first n times we call connect, let's assume that we construct a tree of height log n. Then let's say for the remaining n squared minus n times connect is called, it takes us on the order of log n. Okay? So what we can say now is that the runtime of the add to WQU method in this situation that I've contrived is roughly on the order of n squared log n, right? So what we can say is that a tight big O bound is going to be n squared log n, right? Okay. Let's move on to the next example. And if you guys have any questions, you guys can feel free to post on that because I know this problem is pretty tricky. So for the remainder of this problem, let's suppose that we have a modified version of add to WQU as defined below. And the only difference is now we have this if condition. What this if condition is saying is we have the method size, which calculates the size of the largest connected component. Okay, so we're going to keep executing this for loop, right? We're going to keep executing this for loop until the size of the biggest connected component is equal to elements.length. In other words, what this is saying is that the elements are all connected, right? Because if the size of the largest tree is equal to elements.length, it means that there's a tree with everybody included, which means all the elements are connected, okay? So what I'm going to say now is let's explore two possibilities. Let's explore a possibility for an omega bound. I'll prove it's a tight omega bound. Then let's explore a possibility for a big O bound, okay? But I'm going to start with omega. So when we want to approach omega bounds, how we want to do so is, let's say that our function is as fast as possible, right? For our function to be as fast as possible in this situation, we want to hit this return as quickly as possible, right? We want to exit this for loop because this for loop is taking too much time. So for us to hit this return, it means that we hit this condition, which means that all the elements were connected together. Okay, so for all the elements to be connected together, it means that we called connect at least once on every single element. Okay, so what that means is that we needed at least n/2 connect calls, right? In order to return, it means that all the elements must be connected, which means that we must have called in connect on every single person once. And every time we call connect, we pass in 2 people. So we know that we need at least n/2 connect calls, right? And what that tells us is that since each connect call runs in omega of 1, the fastest that we can possibly exit the add to WQU method is going to be on the order of n. Okay, so we know that this is a possible big omega bound, but now I'm going to show that it's a tight big omega bound. Okay, to show it's a tight omega bound, what I'm going to do is I'm going to construct an example that takes n time. Okay, let's proceed with such an example. Suppose that we have the following elements 0, 1, 2, 3, all the way up till n. The example will work as follows. Let's say that we take the element 0 and then we connect it with 1. Okay, what we're doing is we're calling connect of 0, 1. That's the first thing we do. Okay, I'm going to move this down here. The second thing that we're going to do is we're going to call connect on 0, 2. Okay, so now we have this component right here. And I'm going to assume that the tree I'm building is such that 0 is the root. What that means is it looks something like this. Okay, I realize my face is in the way, so I'm going to move that down. So it looks something like this. This is a tree that we're building. Okay, so now when I call, let's do the next operation. I'm just going to keep calling 0 with every single element in this array. And what we will notice is that all of these calls to connect take us constant time, because we're connecting 0, who's a root, to another element who's also a root, right? Because all of the elements, like 4, 5, 6, they're all roots of their respective trees, since they're the only person in their tree, right? So what we can say is that if we look at all of these connect calls, it'll be on the order of n connect calls, right? And if each connect call takes us constant time, what we can say is that we have constructed such an example where we run in omega of n, or we run in n time, so we know a tight omega bound is omega of n. Okay, so let's now explore the possibility for the big O bound. Okay, I'm going to use a line of reasoning saying that if I can say that we perform on the order of n squared connect operations, on the order of n squared of these operations, then I can use the same logic from the previous part to conclude that the tightest big O bound is n squared log n. Okay, all I have to show is that there's a construction of such a connect operation, or there's a construction of such a pairs array in that we perform on the order of n squared operations. Okay, so suppose that after shuffling the pairs array, the pairs are ordered as follows. I'm going to get rid of some of this stuff right here. Suppose that we have the elements 0 to n, right? And my pairs array, after getting shuffled, has a bunch of pairs, right? And I'm going to say the last n pairs all involve the number 0. Okay, so what I'm trying to create here is that the first time we see the number 0, is in the last n operations, right? Because we know 0 is part of n pairs, so the latest we can possibly see the number 0 is in the last n operations, which means that if we look at all of these operations, there's n squared minus n of them, right? What we can say is that we will never hit this if condition in any of these operations, right? Because in order to hit this if condition, we have to have connected 0 to the tree at some point, right? But the first time we see 0 is in the last n operations. So what we can say is that they are n squared minus n operations where we call connect, right? So there's on the order of n squared operations where we call connect. So what we can say for a type big O bound is big O of n squared log n. Because we're using the same logic from the previous part, and I've constructed a situation in which we perform on the order of n squared connect operations, which is the same logic as what we did before, okay? So let's finish it off with defining a matching size connection as connecting two trees, i.e. components in a weighted quick union together of matching size, okay? So what this is saying is suppose we have the tree 1, 2, and we connect that to the tree 3, 4, okay? This is called a matching size connection because both of these components are of the same size. So what is the minimum and maximum number of matching size connections that can occur after executing add to WQU? We may assume that n, i.e. elements.length, is a power of 2. Okay, so let's try to explore the minimum case first, and I'm going to use the same example I used in the big omega case from before. Okay, so suppose that we have the following elements, okay? And what I'm going to do is I'm going to keep calling connect on 0 and I, and I'm going to call that for all I. Okay, this is some math notation. But in essence, I'm just doing the same thing I did for the omega case before. I'm calling 0 and 1 connect. Then I'm calling 0 and 2 connect, 0 and 3 connect, and so on. And what we will notice is that this is the minimum case because the only matching size connection we have is the first connect call when we do connect of 0 and 1. This is the only matching size connection we have, right? So there's at minimum one matching size connection, right? And I'm going to explore the maximum case, but I'm going to first prove that this indeed is the minimum. Because in any sort of series of connect calls, we need at least one matching size connection, the first one. So since there's no other matching size connections after the first one, we know for a fact that 1 is the minimum, okay? So what is the maximum then? The maximum is going to be in this following possibility. It's going to be similar to merge sort, okay? What we're going to do is we're going to continue connecting neighbors together, okay? So we're going to connect 0, 1, we'll connect 2, 3, we'll connect 4, 5, we'll connect 6, 7. Accordingly, we get the following groups. And notice that these are all matching size connections. So far, we've done 4 matching size connections. Okay, I'm just going to say matching size connection, okay? Then let's keep connecting these two together. And now we've done another 2 more, and we have the following groups. And we've done 2 more matching size connections. And then finally, we do 1 more at the end. And then we see that everybody is connected together. Okay, so in this possibility, the total number of matching size connections we do is 7. And if we look at n, in this case, n is equal to 8, we see that that's the same as n minus 1. Okay, intuitively, why it comes out to n minus 1 is that in this first row, we're doing n over 2. In the second row, we're doing n over 4. In this next row, we're doing n over 8 all the way up till 1, right, if there's more rows. And we know that this sum is equal to n minus 1, right? So this is the maximum number of matching size connections we can possibly have because every connection is a matching size connection, okay? And that is all for this video recording. I hope you guys found it helpful, and yeah, have a good rest of the day.